Intermolecular forces. Intermolecular forces are forces that we find between molecules. Let's say, for example, we put water inside a container. So it is very much impossible to have one molecule of water inside a container. But instead, you are going to have millions and millions of water molecules that are attached together because of these intermolecular forces. So the intermolecular forces are forces that keeps molecules together. So now this water, it is water because now it has the intermolecular forces that is keeping the water molecules together so that it can become a liquid as it is. But now, let's say, for example, we want to break these intermolecular forces. For you to be able to break the intermolecular forces, you need energy. So the more energy you put in this container, the more you're going to give energy to the water molecules, and then they will start to have a high kinetic energy. The more they have high kinetic energy, the more they will want to move away from each other. So when they want to move away from each other, they are going to break these intermolecular forces. But now, there's a point that we need to reach before the intermolecular forces are braked. And that point is what is called now the boiling point. So now the boiling point is a temperature when liquid changes to a gas. So now at this point, when we reach that particular temperature, that means now at that temperature, that is when now the intermolecular forces will start to break. And then when they break, we are going to now transition from a liquid phase, and then we will have now a gas phase. So this means now the water molecule will start to move away from each other. They will only move away from each other if the intermolecular forces are braked. And then we can only break the intermolecular forces if we can reach, for example, the boiling point of a liquid. But now, if we wanted to move now from a solid to a liquid, we will now need to reach what we call now the melting point. So now, in this case, for us to be able to reach the boiling point, there's something that we need to overcome. And this is called now the atmospheric pressure. So the atmospheric pressure, it is the pressure that is keeping the liquid together. But now, if we start to heat up this liquid, what we are doing, we are increasing the vapor pressure of the liquid. So we are increasing the ability of this liquid to become a vapor. So now the more we heat it, remember we give this a kinetic energy. So the more the kinetic energy, the more they will want to do what? To go out. So that is when we call now we are increasing the vapor pressure of what? Of this liquid. So now when the vapor pressure is high enough, or it is at the point whereby it is equal to the atmospheric pressure, that is when now we have reached now that particular temperature, which is called now the boiling point. So at the temperature whereby the vapor pressure is equal to the atmospheric pressure, that is called the boiling point. So let's say, for example, now a substance, it is already having a high vapor pressure. So now do you see now if a substance, it has a vapor pressure that is very much high. So let me just say, for example, we had that pressure there and this pressure there, but now this one is a little bit shorter. So do you see now the vapor pressure of this liquid, it is very high. So we need now less energy so that the vapor pressure can be equal to the atmospheric pressure. So the higher the vapor pressure of a liquid, that means we're going to have now the low boiling point. So that means now we have now the low boiling point, because now it is very much easy for us to reach that boiling point, because we will have to now equate the vapor pressure to the atmospheric pressure, and that is very much easy since the vapor pressure, it is already high. So now at the point whereby we have a high vapor pressure, we are going to have the low boiling point, because now we need less energy to overcome those intermolecular forces, and then we can transition now from a liquid to a gas. But now, if a substance is having now a less vapor pressure, what is going to happen is that, let's assume that the vapor pressure of this substance is just only 1 vapor pressure. Then you will see now we will need to heat this liquid at a very much high energy so that we can increase the vapor pressure of this substance, and then it can be equal to the atmospheric pressure. So if initially the vapor pressure of a liquid, it is very much low, so that means we're gonna need a high temperature so that we can reach the boiling point. So that means now the boiling point, it is going to be very much high. So the lower the vapor pressure, the higher the boiling point. And then remember now, the higher we have to reach the boiling point, that means we need more energy to overcome these intermolecular forces so that we can transition from a liquid phase to a gas phase. So this means now we need now a high energy so that we can break those particular bonds. This theory that I've explained here, it is very much important. You need to understand this theory so that you can answer it on your exam papers. Please feel free to pause the video and repeat this part so that you understand it properly before we can move on now to the types of intermolecular forces we will find in organic chemistry. So now, in organic chemistry, we are going to focus on 3 types of intermolecular forces. So the first intermolecular forces is a intermolecular forces that we find between now non-polar molecules. Let's say, for example, we have now 2 methane molecules that are attached together by a particular intermolecular forces. So we already know that this methane here, it is having a non-polar. And then if this is a non-polar, that means also this other molecule of methane will be a non-polar. So if we have a non-polar and a non-polar, that means now what is going to happen is that we're going to have these weakest forces in between the molecules, and those weakest forces, we call them the London forces. So remember now, this methane is a non-polar because now if we look at the electronegativity of carbon and hydrogen, remember now the carbon, it is having high electronegativity. That means now the electrons between the hydrogen and the carbon will move closer to the carbon. So that means now the net moment will be in the direction of the carbon, but this will happen also on the other side, and it will happen on the other side, and then it will also happen on the other side. And then at this point, all these net moment, they are going to cancel out each other, and then we are going to have a non-polar molecules. So that is how we know that a methane is a non-polar molecules, because now these electronegativity differences will cancel each other out. So we said now we have now the London forces, and the London forces are actually the weakest intermolecular forces that we are going to have. So another type of intermolecular forces that we're going to talk about, it is what we call now a dipole-dipole intermolecular forces. So let's say, for example, we were having, I'm just going to make a typical example, whereby we have now a carbon that is bonded now to different hydrogens, but now at this side, this carbon, it is bonded to a halogen. Let's say, for example, we have a bromine. Okay, so now if this molecule, it is bonded to now the same molecule, because now you can't have an intermolecular forces to one molecule. You need now more than 2 molecules to have the intermolecular forces that is connecting those molecules. So if we look at this, we are going to have now a electronegativity difference that is in between the carbon and the bromo, to be way much higher than the one that is in between the hydrogen and the gas. So that means that we're going to have the polarity in this direction, whereby now on this part here, the polarities will cancel out each other. But now in the horizontal part, the electronegativity difference is going to be there. That means now this a molecule here, it is going to be a polar molecule. So now if we have a polar molecule bonding with a polar molecule, we are starting to have now what we call a dipole-dipole forces. So the forces that will be in between this molecule, we are going to call them a dipole-dipole forces. So dipole-dipole forces are actually stronger forces than the London forces. They are very much strong. But now, if we have another type of intermolecular forces, now which we call now the hydrogen bond. So the hydrogen bond is a form of what? Of a dipole-dipole intermolecular forces, but now is a special one whereby, let's say for example, we replace now this bromine here, and then we replace it now with a hydroxide. So now you will see now the dipole-dipole, it is still a dipole-dipole, but now as soon as we have a hydrogen bonded to an oxygen, or if we have now a hydrogen bonded to nitrogen, oxygen, and fluorine, we are going to start to have what we call a hydrogen bond. So now the hydrogen bond only appears if we have now hydrogen bonded to oxygen, or bonded to nitrogen, or bonded to a fluorine. So now in this case, on our organic chemistry, we will see now the hydrogen bond, it will appear now where we have that hydroxide, whereby oxygen, it is bonded to a hydrogen. So now this now, it is going to become the highest or the strongest intermolecular forces, which are called now the hydrogen bond. So now the hydrogen bond are what we call now the strongest intermolecular forces that we can get in between molecules. So now we have what? We have London forces, we have dipole-dipoles, and then we have hydrogen bonds. So now the hydrogen bonds are the strongest, and then now dipole-dipole are second strongest. But now when you look at the London force are the weakest forces in this part of organic chemistry. So now let us look at now the intermolecular forces that we will find in different structures. So now remember now, we are going to talk about organic chemistry, and then these homologous series are what we need to understand. Let's say, for example, we want to look at the difference between the intermolecular forces of an alkanes. So if we look at an alkane molecule is going to consist of what we call the London forces, because now you can see now the electronegativity differences will cancel out each other because these molecules are symmetrical. So that means now the forces that we will get now in between these alkanes is going to be London forces. So now remember now the London forces are the weakest forces that we get. But now we can also compare now the difference in what? In the London forces. So if you look at this one here, we have the longer chain than this part here. So the longer the chain, the more we're going to have a lot of London forces that is connected in between the molecules. So that means now these London forces here are stronger than the London forces that are having a less chain. So this one are what? Are going to be weak London forces. So remember now, I'm saying they are weak London forces, and then this one are stronger London forces because now they have the highest surface area. You can see now the chain is longer. So the longer the chain, the more we're going to have these intermolecular forces. So the stronger or the high energy we will need to break these intermolecular forces, because it is a lot of them. But now if we have a less chain, we are going to have now less intermolecular forces. So that means you're going to need now less energy to break each of them. But now if you look at this one, there's going to be a lot of them since now we are having a larger surface area. So now the larger the surface area, the larger or the stronger the intermolecular forces. But now we also need to look at now if we have a branched. So now if you look at this part here, in this part here we have now the same chain as this part here. But before we can discuss this part here, let me just say now, let's look at this part A and this part here, which is now named B. So if we look at this part here, this is the only way we can now make the comparison. If the number of carbons are the same, you see now at this chain, we have 4 carbons, and then also on this part, we have 1, 2, 3, 4 carbons, even though it is branched, but now we have equal number of molecules. Equal number of carbons. So if that is the case, then we can make a fair comparison. We will say now, if ever we have the same number of carbons, but now this part here, it is branched. The more it is branched, and then we have the same number of carbons, that means now we are decreasing the surface area when we branch it. But remember that if the carbons are the same, that is when we're going to decrease what? The surface area. So that means now this is going to have weak intermolecular forces than B. So that means now B is going to have the strongest intermolecular forces, even though they have what? The same number of carbons. But now this A here, it is branched. So if you branch it, that means you increase the contact area. So the less intermolecular forces we're going to find. So that means it's going to be now the weak intermolecular forces because it's going to be easy to break them. But if you look at this long chain, we're going to have a lot of intermolecular forces. So it's going to be difficult to break them. So the stronger intermolecular forces, we're going to find them in this long chain. But now you must also note something. If we look at now A and B, A and C, this C here, it is going to have something different. So if you look at this now, C here, it is having 3 carbons. But if you look at A, it is having 4 carbons. Even though now A is branched, but if you look at this, A, it is going to have more number of molar masses than C. So even though it is branched, it is going to have high intermolecular forces than C because now it has high molar mass. It is not a fair comparison because now we have more carbons than on this part. But now if the carbons are the same amount, then if something is branched, it's going to have what? Weak intermolecular forces because we have decreased the surface area. But in this case, we have decreased the surface area, but we have also now increased the molar mass if we wanted to compare now to C. So that means now A is going to have the stronger forces than C, even though now A is branched. But now if the number of carbons are the same, that means now A is having the higher molecular mass, therefore the stronger the intermolecular forces. So now when you compare the intermolecular forces between alkanes, you will see now you will have to use now these long chains and also the branches. And I hope what I've just explained, it makes sense to you. So now if we move on now to talk about alkenes, if you look at alkenes and alkynes, we are going to also have now the London forces because now this thing here, it is symmetrical. Somewhere, somehow, these bonds will electronegativity, we're going to cancel out each other together, and then we're going to only have the London forces. So now in both alkenes and alkynes, we have London forces. But now if you look at this, because of the double bond shape, the London forces on alkenes are much stronger than the London bonds that we get on alkanes, because on alkanes we don't have the double bonds. Then if you look at this now, on alkenes, we have the triple bonds. So because of these triple bonds, the intermolecular forces are going to be much stronger than the one of alkenes, because now the triple bond are going to have stronger London forces than this one of the double bonds. But now remember, now the comparison will also be the same when we look at now the amount of chain and the amount of carbons that we have. Okay, the very same thing that we have done in what? In the alkane part. If you look at this part here, already we know that this part of A, it is having a stronger London forces than B, even though they would have now the same amount of carbons. But now if you look at this, now we have a longer chain. So the longer the chain, the more intermolecular forces you need to break. So that means now the stronger the force, even though it was going to be the same alkene and alkenes. So also remember about the chain. The chain plays a very huge role when you come to intermolecular forces. So now we're going to move on now to talk about intermolecular forces between haloalkanes. So we already talked about the haloalkanes. If you look at this now, on this region whereby we have a haloalkanes, remember now we're going to have a dipole-dipole forces. So we have now dipole-dipole forces. But you will also see now on this other parts of the carbons, we are still having what? The London forces. So now inside haloalkanes, we have a dipole-dipole forces and we have now London forces. So that means now this dipole-dipole or haloalkanes are way much stronger than alkanes, alkenes, and alkynes, because now they have this type of forces which are stronger, which are called now dipole-dipole. But now, if we go and look at alcohol, if you look at an alcohol, it is having this part here, which we call now a hydroxide. So remember now, the minute we have oxygen bonded to hydrogen, then we're going to have the hydrogen bond. So now inside the alcohol, we're having what? We're having now the hydrogen bond, of which these are now the strongest bonds we can get. These are the hydrogen bond, are the strongest intermolecular forces. But now inside the alcohol, we have the hydrogen bond and we also have the London forces. So now we have now the hydrogen bond and we also have the London forces. So if we were to compare the alcohol with the haloalkanes, we will say now alcohols are way much stronger than the haloalkanes because now they have this type of bonds that are very much strong, and those bonds we call them the hydrogen bonds. I mean those forces, which is now a hydrogen bond is an intermolecular force. So they're going to have the strongest intermolecular forces than haloalkanes because the hydrogen bond forces are way much stronger than all this type of other intermolecular forces. Okay, so now if we look at now aldehyde, if we look at an aldehyde is going to have now what we call a dipole-dipole, because now if you see here, we're going to have what? We are going to have now a non-polar, a polar and a polar at that point. So now if we have two polars at this portion, then we're going to have what? We're going to have a dipole-dipole. Please be careful, this is not a hydrogen bond, because now you see now oxygen is connected to a carbon. It is not connected directly to hydrogen. It is only a hydrogen bond if the oxygen is connected directly to a hydrogen atom. So now what we have in this case, we have now what we call dipole-dipole forces. And then now after dipole-dipole forces, you will also see that we have now this London forces. So we're going to have now dipole-dipole and London forces. So you will also see now the what? The alcohol is going to have the strongest intermolecular forces because now they are having the hydrogen bond. And then we saw now, remember now the hydrogen bond are the strongest intermolecular forces. So this part of aldehydes, it is only having dipole-dipoles and London forces. So alcohol will be much stronger than those aldehydes. So now if we were to compare now the aldehydes and ketone, we are going to get the very similar thing, because now at this point here, we are having that dipole-dipole, and then we're going to have now also this part of London forces. So in the ketone and aldehydes, we will have now dipole-dipoles, and we will also have those London forces. Okay, but now if we move on now to what we call now the carboxylic acid. If you look at the carboxylic acid are the one that are going to be the strongest one. Look at why they are the strongest one. If you look at this now, we have now this part that we are talking about whereby oxygen is connected to a carbon, and then that is making a dipole-dipole, since we're having a non-polar, a polar and a pole. So we're going to have what you call now a dipole-dipole in that portion there. But now, if you also look at this part here, we are having now this oxygen connected to hydrogen, and then we're going to have a dipole-dipole. But now that dipole-dipole in that part is going to be special. And that dipole-dipole is going to be what? It's going to be a hydrogen bond, since we have now oxygen being connected to the hydrogen. So we have these dipole-dipoles. We have also now what we have hydrogen bonds, and then we also have these London forces in between the other molecules. So you see now in the carboxylic acid, we have a dipole-dipole, we have hydrogen bonds, we have London forces. So that means this one are the strongest of them all, because now they have all this type of forces. We have now the hydrogen bond, we also have the dipole-dipole, we also have the London forces. If we were to compare this carboxylic acid to an alcohol, you will see now in an alcohol, what do we have? In an alcohol, we only have what? We only have the hydrogen bond and the London forces. So now the carboxylic acid will have the strongest force, since they have now the hydrogen bond, they also have the dipole-dipole, and they have the London forces. But now if you look at alcohols, they only have hydrogen bonds and London forces. So now at the last stage, we're going to now look at what? We're going to look at esters. So when you talk about an ester, we can clearly see now, if we will look at ester, we're going to have now this dipole-dipole forces here. Do you see now we're going to have a dipole-dipole forces? Remember now, this dipole-dipole forces is not a hydrogen bond, since oxygen is not connected to a hydrogen. So we're going to have dipole-dipole forces. And then we're also going to have what? We're also going to have now maybe small dipole here because of the oxygen there. But we're also going to have now these London forces. So in esters, we have what? We have dipole-dipole, and we also have now London forces. So you can clearly see now the carboxylic acid will have the strongest intermolecular forces, because now they have the hydrogen bond, and the esters don't have the hydrogen bonds, but they have what? The dipole, and the London forces. So I hope what we have discussed, it really makes sense. So now if you were to compare now these forces in terms of the following groups of organic chemistry, you will see now the London forces are going to come now in this direction. We say now the alkanes are going to be the weakest one. And then the alkenes are going to be stronger than the alkanes because of the double bond between the carbon. And then now the alkenes are going to be stronger than the alkanes and alkenes because now they have the triple bond between those carbon. But all of this one of alkane, alkenes, and alkynes, we only have the London forces. And then now the one that is going to come after that, it is what we call now an ester, because now an ester, it is having a dipole-dipole and only London forces. And then if you also look at aldehydes and ketones, they're very much similar. They also have what? Dipole-dipole forces and London forces. But you also need to note that the aldehydes and ketone are very much stronger than the esters. So esters are the weakest after the group of hydrocarbons. So now if you look at this, the haloalkane will be way stronger than the aldehydes and ketone, because now they are going to have the strong London forces because of that halogen. So they have the dipole-dipoles, but now they have now the strong London forces more than this part. And then now if you look at alcohols are going to be stronger than the part that is at the top, because they have the hydrogen bond and they have what? The dipole-dipoles, and they also have the London forces. But now if you look at the carboxylic acid, we have what? We have strong hydrogen bond, we have dipole-dipoles, and we have London forces. So now the reason now we put alcohols with dipole-dipole forces is because now whenever you have a hydrogen bond, the hydrogen bond is coming from the dipole-dipole. So automatically you have what? A dipole-dipole if you have a hydrogen bond. And then you're also going to have again now that hydrogen bond, which makes it to be way much stronger. So this is what I have for this video. Thank you very much.